Hi, I'm Mark Wardle. I'm a consultant neurologist. I'm going to talk about using the principles of Clojure and Clojure itself to unbundle the electronic health record, to reimagine what we think of as the electronic health record and turn it inside out. So the traditional or conventional EPR is viewed in the context of as an application, as a system. It's a healthcare provider will buy it in, deploy it, maybe integrate it with other systems. It's centered therefore on the organization that's buying it, and it tends to be focused on process, measures of process, and billing, depending on where you work in the world. So internally, at least, it's regarded as a monolith. And that's certainly the case for most of the EPRs. The insides are therefore proprietary, and it's independent from other applications, but at the application level. So you might integrate that application, but it's kind of like a combinatorial explosion because you've got to try and link all of these things together. They may use standards, although they may not. And there's some really important exceptions where they don't use standards. But if they do, they're externally facing, so they're in the interfaces to other systems. So they have external interoperability, but interoperability internally doesn't really, it's not the lingua franca of the internal system architecture. The boundaries, therefore, are based on the organisation or for billing who pays, and therefore the interactions when you deploy are kind of ossified, fossilised, and static. So you deploy, we've got to integrate it with our laboratory system, so someone does some work to do that. So you end up with a lot of concretions in your environment, in your enterprise. You'll have a patient portal, you may have population health analytics, you've got your EPR. It's highly specific, and the data is there within the application. It's changed within the application. It's in buckets within the application. Data is in the context of the application. If you want to do other things like population health analytics, managing your service, or doing research, you kind of take the data out and you process it in a different way. It's not embedded necessarily, and therefore you end up with tooling that's quite separate. So your EPR might be built with .NET or Java, C#. Your analytics might be proprietary or built into dashboarding. It's kind of locked in, or you do R and Python for your research. And so if you're going to be using algorithms, using trying to analyze your data, you're going to do it in a different way, whether it's direct care analytics or research, which kind of doesn't make any sense. So when I talk about unbundling the EPR, I'm talking about focusing on the data, using self-describing data, so adopting FAIR principles, which are findability, accessibility, interoperability, and reusability. And so actually our data becomes much more focused on the patient and not the organisation. In fact, you could see a situation where you could compose data very easily from multiple organisations because it's data's first class. It just composes really nicely, irrespective of the organisation. We can therefore focus on not just measures of process, but actually start to think about measures that are much more meaningful to a health and care system, like outcomes. Our architecture, because we focus on data, is by definition distributed. We're programming the insides of our systems just like we program the outsides. And of course I'm quoting Learning from Systems by Rich Hickey, where he talks about RPC and queues and just plain data. Why don't we do that in health and care more? So the idea, therefore, is that you can build a suite of computing and data services that are essentially independent, but can be composed together to be used to solve user problems. And that means making standards ubiquitous internally and externally. We have interoperability on the insides of our systems as well as on the outsides. So our boundaries are based on our domain. The complexity of the health and care domain mean you do need boundaries. You need to break apart health and care and then recompose it back together. But that should be aligned to our domain. It shouldn't be aligned to organisations. When we have discrete computing and data services that we orchestrate together, we benefit from being dynamic and extensible, and we work to abstractions. We don't really care about the implementation details. When we consume those services, are talking about generic services that are in the abstract. We start to model first-class events, and we start to model immutable data. And actually that fits very nicely with health and care data. Our old paper records were always immutable and ever accumulating. Our data, therefore, in an unbundled EPR is both in buckets and is moving around. It's orchestrating workflow and process across organizations, so it's flowing, it's self-describing, domain-orientated. And of course, health and care has tried to focus on data and interoperability for many years. One approach, so this is in London here, we've got Guy's and St Thomas's and we've got King's College, and those two organisations want to work more closely together, so they are adopting an approach of interoperability through convergence by adopting the same underlying application, a single shared application, EPIC. So they want to make it easier and quicker for staff to access a single source of information. They want to reduce the number of different IT systems in place, so they're converging. That's one approach. The Royal Free, however, uses Cerner. So how do you do that? Do you converge them and rip that out and replace? No. So across London, they're talking about building a wider health information exchange. That will extract data, transform it and standardise it in the external to create a kind of cut down shared cared record. So it won't have all the detail, but it'll have some documents and some core information that can be shared across London. So that's interoperability through standards and information exchange. It's not a bad approach either, but it is cut down and doesn't really solve analytics. So there's not a level of granularity to the data that allows you to do population health analytics, for example, and certainly research is still external to all of that. It's still a separate program, really. And of course, you can start to try to tease apart what we think of as the EPR. You can kind of understand it in terms of its domain. So radiology or a staff index, who works for whom, which patients which, what reference data, classifications, terminology. If you start to break it apart on the domain, it starts to get easier. But each organisation at the moment has all of these inside them. So number one up here is the shared single instance. Number two is where we're doing a limited, transformed, standard-based exchange of information. But for patients and clinicians, it still feels very fragmented, and we still have a problem of a lack of shared semantics. For example, what if there's a staff member who works across multiple sites? We need to know that that staff member identifier up in that organisation is the same as that one there. The semantics of the information are actually what really matter. And for the poor patient, it feels very fragmented as well, because often they'll use a patient portal that's still linked into the underlying EPR. So depending on which organisation they are going to, they may need to access a different portal. So that's unsatisfactory. Clojure can teach us a lot. Clojure is a great language for implementation. I can use it now for building applications for direct care, for analytics pipelines, and I can use it in research. It's powerful, it's expressive, and it's concise. But perhaps the most important thing health and care can learn from Clojure are the core principles. You know all of these. It's data orientated. Data is data. It has first-class names. We work to abstractions. It's functional. That's a great fit for health and care. We need reproducible data pipelines where we get the same outputs from the same inputs, and functional programming languages give us that. Clojure favours immutability and manages explicit state. Again, that's very important in health and care. We have loose coupling between systems. It teaches us to be dynamic and flexible and adaptive to change. Health and care is always changing. It models first-class events, and it teaches us to build the internals of our system as in the large. So the third way is interoperability through composition and layering of domain-aligned data and software components. So many hospitals have electronic prescribing and medicines administration, or EPMA. Imagine a situation, I'm in a hospital and I've got, I want to monitor all the antibiotics that are prescribed. One of the options I can do, option 1, is to perform analytics using the services, the analytics bit that the EPMA or EPR vendor give me. And that's okay. It works for kind of that system, but many hospitals have different prescribing systems for chemotherapy. Many enterprises have community services which will be on a different system. So we've got general practitioners in the NHS in the United Kingdom, and you may have specialist EPMA services in some clinical domains like critical care. So actually building your analytics and relying on the analytics in a single system doesn't really work. Not if you want a kind of population level analysis. The other option 2, is to take all that data and try to put it into some kind of health information exchange. That kind of can work. The other way, the third way, is to unbundle the EPR. So what that means is we take a feed of data, and many suppliers will be able to feed us data in a standards-based way, and some will not, and we'll have to transform it and extract it properly and turn it into first-class, well-defined, self-describing data as an event stream. Now, we can take that event stream and annotate it. And if we have a suite of computing and data services which give us access to terminology, which give us access to drug dictionaries, we can do lookups against the drug codes that are in that event stream, annotate our information with really meaningful information, maybe about laboratory data, maybe about the drug itself, and then create substreams of that information that other consumers can subscribe to. So for example, an antimicrobial event stream could then be used to populate a real-time dashboard. We are really turning what we think of as the EPR inside out and making our data first class. This relies on a suite of first class composable data and software services, but we can use that then for direct care in managing that patient when we're seeing them in the clinic or on the ward, but we can also use the same tooling but composed in different ways for our analytics and for our research. So one of the things that I think is really important is making sense-making from health and care data. And so that means using a terminology. And one of the big terminologies in health and care is SNOMED CT. And so I've built tooling relating to SNOMED CT in Clojure. And I think it's really helpful for building software systems that can be dynamic and deal with changing data over time. So the example here is specialties, but it could apply equally to ICD-10 diagnostic codes. So on the right-hand side here, we've got just a flat list. There's no structure here of medical specialties. So we've got neurology and pediatric neurology and pediatrics. So there's no real relationship between those codes. It's a flat list. So if I'm writing software to try to understand that, I could build that in, but it's not extensible. And also in code, therefore, I can't really work out that pediatric neurology is actually a type of pediatrics or a type of neurology. It's kind of just concrete, it's a list. SNOMED CT, on the other hand, has meaning behind it. It is an ontology. It's not perfect, but it does mean that whether it's a diagnostic code or medication code or a specialty code, there are lots of different categories, I can make inferences, and if a new specialty is created, my code does not need to change. So pediatric neurology is a type of neurology, and neurology is a type of clinical specialty, etc., etc. So if we build software that gives us the capability to take codes like this, make sense of them, we can build compelling user experience in direct care, but also make the most of that data in our analytics and in our research. We did this, so the European Medicines Agency had a problem with one drug in multiple sclerosis, so we rapidly needed to build a portal for letting clinicians record patient data, and so we used the same tooling to build that platform, but then also the same tooling to build the data analytics and research side as well. All the same code, just composed in different ways, and all built using Clojure. So here is here's one element of it. So this is fast auto completion of SNOMED CT codes. Here we're just asking for a diagnostic code, so we're not giving all of SNOMED CT. We just limit it, but we can use the same tooling across all of the different uses. You can enter codes using pick lists or drop downs or auto completion or clicking on pictures of anatomy, all kinds of different structures. But then we can make use of that data in our pipelines. So when we're trying to make sense of that, we often need to transform that information and turn what is real life, complex, hierarchical data into a projection, a rectangular projection that makes things much simpler to understand. So for a certain project, so for this one we had well-defined, publicly defined kind of criteria. Does this patient have a type of respiratory disease or autoimmune disease? So using Clojure and the tools I've built, we could then say, well, here's Graves' disease. We could then pass this, transform it and say, well, is this a type of endocrine problem? Yes. Is it a type of autoimmune condition? Yes, it is. And so that just really facilitates the analytics pipeline, allows us to sense make of complex data, give it a rectangular projection, which will vary. That projection will vary depending on the needs that we have at the time, and it's great to delay that. So rather than trying to record it up front, is we record granular information up front and then derive these kinds of projections later using Clojure. So this is the kind of architecture. So at the top I've built a few different applications, and they use Wilke Lucchio's Pathom Graph API to make use of these composable services. So I've got code lists which can kind of declaratively define lists of codes for different criteria and then apply that into health and care data. Hermes, I'm going to talk about in a minute, gives us access to all of SNOMED CT. I've got DMD, which is the UK Dictionary of Medicine Devices, and so on. All these back-end services provided to make sense of data in context. So the Graph API allows me to write concrete services but look at them in the abstract. So request properties based on X500 or HL7 FHIR and have that query satisfied by transforming the underlying source data from wherever it comes. So different UK services. What's missing from here and what I plan to build is ongoing higher value components for decision support and design systems to make the applications kind of lightweight and ephemeral and really focused on delivering value. In the last 5 minutes, I'm just going to give a quick demonstration of just a couple of the tools. The first is Hermes, which is gives me access programmatically to SNOMED CT. I use it via the Graph API, but I can also use it just from Java or Clojure. So I've just got a REPL set up here, so I can load up my SNOMED database. I can For testing, you can just kind of generate some of the SNOMED CT core components. That's been brilliant for making sure I've kind of tested all the edge cases. SNOMED CT is enormous, so it's got over 1 million different kind of concepts, including diagnoses and medications. It's got descriptions in different languages for all of those concepts, and then it describes the relationships between concepts, those kind of ISA, or this disease affects this part of the body. It also organises concepts along reference sets, so mapping from ICD-10 and OPCS and other types of code systems. So what that means in reality is that for any specific code, so here we've got 247.00007, I can kind of call up the UK's preferred synonym for that, and of course when I built tooling in other languages, I had to like build my own browser and almost my own kind of DSL to make sense of SNOMED and browse it and manipulate and check everything was working. But of course, the REPL of Clojure just gives me that for free, so I can just define a function PS, which will give me the preferred synonym. That will give me the code and the preferred synonym for anything then. And within it, I can pull out all of the kind of relationships for a concept. So each of these means something. So this is a, for example. So if I do that, it will tell me is a. And of course, actually, we can use the back-end transitive closure tables to expand our understanding of what multiple sclerosis is. So we can say multiple sclerosis is a type, and it's a type of all of these codes here. Clojure is fantastic for doing this though, because I can take that, I can update the keys and turn that into the name of it, and I can update the values and turn those into the names. So if I just run that, I can say, okay, well, multiple sclerosis is a type of demyelinating disease of the central nervous system. When it comes to trying to deal with health and care record data, this is fantastic because I can make sense of it. It doesn't actually matter. I can say, well, is it a subtype of multiple? It doesn't really matter. Is this a type of motor neuron disease? It doesn't matter. I can make sense of that data. One of the nice things when we're trying to process data is you kind of need to simplify it. So here we've got the UK emergency subset. It's a kind of limited list of codes that we think are important in the emergency unit. One option would be you make all emergency units only record these, let me make it simpler, they can only record these codes, but that doesn't make any sense because there are subtypes of some of these diseases. So my favourite option is always to give clinicians the tools to record very granular specific information. But when it comes to doing analysis, we can then genericize, we can we can map the very granular terms into something that is meaningful at that level. So here is multiple sclerosis, and this here is limbic encephalitis with a specific subtype of antibody. That's very specific. No analytics person would really want to know that. And in fact, that isn't in that reference set. Multiple sclerosis is. But if we do map that, so we can do all this kind of data manipulation because we're just dealing with data. We can see multiple sclerosis is mapped to multiple sclerosis. It's left unchanged. But this very specialised funny encephalitis is mapped into this code here. This code here is actually just generic encephalitis. It's a broad term, lots of different subtypes. That is fine, but that's suitable now for analytics. We can use this data to build really compelling applications and user experiences. So my user type's Parkinson, and we can search for all these terms because I can derive all of the synonyms. So say I do a search for Wegener. Actually, we can look at health records and pull out, say we're doing a free text trawl of patients. We might look for all of these different types of codes and different text in our documents just to make for case finding purposes. We can take Hermes and compose it with other services. So this is code lists. We can take Hermes and my implementation of the UK Dictionary of Medicines and Devices, and we can do something similar. We can look at conditions like this, but now we can use codes. So we can use ICD-10 codes or ATC codes. We can define value sets using these codes, realize the concepts and do intersections and understanding of our health and care data. So for example, if a research pipeline says we need to be looking at code G35, which is multiple sclerosis, I can turn that into a set of concepts and then use that in my tests. But we can also do more. So say for example, we know about the basal ganglia, that's a part of the brain. We know about peripheral nerve, they're the your peripheral nerves innervate your muscles. So these have got codes. We can actually write code which takes any diagnostic concept and says, actually, is this a disease that affects this area? So for example, is G20, which is here, we're going to turn it into a set of concepts, and then we're going to say, is that a type of basal ganglia disease? And it will say yes. But is G20 a type of disease that affects the peripheral nerves? No, it's not. Sorry, I've done that wrong. So no, it's not. But we can say, well, actually, is G61 a type of disease that affects the peripheral nerves? Yes, it is. So having the data and the software to make sense of that data and apply it to data is an absolute superpower. And this is what we've done. So we can then take a study, we can take our real life data, we can define our code lists declaratively and apply that and make sense of our data for data research and analytics. Clojure, I think, tells us a lot about how we can approach health and care data in the future, and I think that it gives us a really valuable set of tools and principles to turn what we think of as the EPR inside out. Thank you.